Okay. Hi, I'm Kelly Davis. The title of my talk is Freeing Speech with Deep Learning. Basically, I'm going to first start with a little outline of the talk. One, I'm going to give a brief introduction to sort of frame the talk. And then two, I'm going to start talking about sort of why Mozilla is dealing with speech and why now. Then I'm going to go into a little bit of a deep dive into the neural network architecture of our speech recognition engine. And then I'm going to talk a little bit about the care and feeding of the engine, sort of what hardware we train on, what data we use to actually train the system. And then I'm going to talk a little bit about our future plans. So first, the introduction. From a bird's eye view, speech recognition is really very simple. It's basically take some speech, feed it to a microphone, digitize it into some form of ones and zeros, do some computation on that, and come out with a transcript. That's a transcript of the original speech. And as you all know, sort of machine learning, deep learning in particular, is a branch of machine learning where the computational units are really sort of modeled off of neurons in the brain. And the talk really today is going to be concerned about the intersection of these two different fields, of speech to text and deep learning. So now one may be wondering why Mozilla is concerned with speech, and also why now. In particular, Mozilla is usually guided by the manifesto. The manifesto is essentially 10 or so guiding principles that we have in terms of just making decisions as to what we do and what we don't do. In particular, principle 2 states the internet is a global public resource that must remain open and accessible. Speech recognition really right now is relatively siloed. There's a few different big companies that have speech recognition engines that are production quality, where there's very little in the open source world. There's very little algorithms, and there's little data to train on, and also basically no open models. And we're aiming to change that situation. Principle 4 states individual security and privacy on the internet are fundamental and must not be treated as optional. Current speech recognition engines are really sort of client-server based. So you have a client, you stream some audio to a server somewhere. The server takes the audio, creates a transcript of it, and sends it back to the client. That really gives you a big attack surface for the sort of privacy attacks and also security attacks. We want to lessen that attack surface by bringing speech recognition onto the client. So basically, we're going to try and create a speech recognition engine which can work on your desktop or work on your laptop or work on even a Raspberry Pi. Another thing we're guided by is principle 7, which says free and open source software promotes the development of internet as a public resource. All our code is open, all our models are open, and the data we're training on is also open. That's hopefully we'll be able to spur sort of development in the speech recognition area by doing that. And finally, I guess to dovetail on the previous talk, magnifying the public benefit aspects of the internet is an important goal worthy of time, attention, and commitment. Most of the speech recognition engines that exist now are for languages that are, let's say, have a lot of economic heft behind them. A lot of other languages, even though they may have a lot of speakers, don't have this economic heft and therefore sort of ignored by current speech recognition engines. What we're trying to do is create the algorithms and data and what have you and open them to the world so anyone can use one of our models or indeed create one of their own for whatever language they see fit. And why now? It's a good time to be doing speech recognition engines. Basically, to create a speech recognition engine, you need more or less like 3 ingredients. You need algorithms, you need compute, and actually you need data. And in the last several years, really, the availability of these 3 different ingredients has really sort of increased a lot. So now is a really good time to be considering and working on speech recognition engines. Now I want to go into a little bit of a deep dive in terms of the architecture of our speech recognition engine, deep speech. I'll start relatively slowly, and then I'll go a little bit quicker. It's not a complex architecture. Basically, the first thing, sort of the softest fly of deep learning is really the feed-forward neural network. Feed-forward neural network has various different layers. Each one of these layers has various different nodes. Each one of these nodes does a simple computation. It takes a vector, multiplies it times the matrix, adds a bias vector to it, and then applies a nonlinear function to the result component-wise. Simple feed-forward neural network. It can deal with static things like images, for example. However, it doesn't deal well with things like time series data, for example, video or audio. To deal with that, you need to consider a recurrent neural network. It's similar to a feed-forward neural network. It has different layers. The layers have various different nodes, but the nodes computation is a little bit different. It does a beginning computation very much like a feed-forward neural network. It takes a vector for this particular time tech as input, multiplies it times a matrix, adds a bias vector, but then it has essentially a memory. For the layer that the node is in, the output of the layer that node is in creates a vector. And one can look at the vector for one time tick before and take this time tick, one time tick before vector, and then multiply it by a second matrix, and add to the result I just talked about before. I then apply a nonlinear function to it. In particular, we're using ReLU for a nonlinear function. But this is basically sort of a recurrent neural network. It allows you to sort of have outputs which are dependent upon the information you're getting at this particular time tick plus past time ticks. So you can actually do a variation of this called bidirectional recurrent neural network. If one is given a complete sequence of data, so from beginning to end, one can view this complete sequence of data as two different ways. One can view it as a sequence forward in time, and one can view it as a sequence backwards in time. One can introduce two different recurrent neural networks, one for the forward sequence and one for the backward sequence. And these pair of recurrent neural networks are together named a bidirectional recurrent neural network. And one can process information with this bidirectional recurrent neural network relatively easily. Now, with that information, one can look at, basically this is the architecture of our speech recognition engine. It actually just contains more or less these components, a few details that I'm glossing over, but I mean the core of it's really right there. The input is basically some audio, which is speech. When one takes basically some features from the speech, we use MSCC features, which are basically glorified Fourier transform, more or less. So you have a vector of features for each particular time tick. They're sent to 3 different feed-forward layers. And after that, it's sent to a bidirectional recurrent neural network layer, another feed-forward layer, and then sent to a softmax output layer. The softmax output layer outputs into characters. So basically, for example, the characters of the language you're dealing with. So in English, for example, it'd be, say, 26 characters plus a particular space. And after that, it's fed to what's called the CTC algorithm. I'm not going to go into detail about that, but the basic idea of it is it solves the alignment problem. Okay, one can think of saying a particular audio sample. One could say a particular sentence very slowly or very quickly. However, the audio sample for both of these has different lengths. One's very long and one's very short. However, the transcript for both of these is the same. So one has to align these varying audio lengths to actually the same transcript. And this is the alignment problem. The CTC algorithm, I guess it was introduced by Graves in his PhD thesis several years ago, solves this alignment problem. And this is the core, really, of our speech recognition engine. It has a few other aspects to it in terms of, say, language model and the like, but I'll gloss over those for now. Now I'm going to talk a little bit about the care and feeding of the system to give you a sort of a feeling for some of the numbers that we were talking about in the previous talk in terms of the data required and how long it takes to train the system. I'm talking briefly about the algorithms before, so now I'm going to talk about the compute required to actually train the system. What we have is a small cluster, a relatively modest cluster, I'd say. It has a head node and has 4 worker nodes. The head node itself has 100 terabytes of disk to store the audio to train on. Each of the worker nodes has 8 Titan-X Pascal GPUs. Each one of those has about 11 teraflops of compute in it. Each one of the nodes also has 128 gigs of RAM, and the whole thing is connected together in 10 gigabit networking. So basically a modest cluster. To give you a feeling for how compute heavy this training is, if you have about 3,200 hours of data, this whole cluster will take about a week and a half to actually train a model on. So it's pretty compute intensive to actually do this. And now talk a little bit more about the actual data to train our system on. Data is one of the biggest, I guess from the previous talk, one knows that data is one of the biggest problems for speech recognition engines. Obtaining transcribed data is super costly, or getting open source data basically doesn't exist. So what we initially did is we purchased 2 data sets to start with. We purchased the switchboard corpus and the Fisher corpus from Linguistic Data Consortium. Together that's about 2,200 hours of audio data transcribed. And also we use the biggest open source speech corpus, which is LibriSpeech, and that's about 1,000 hours. So together this is about 3,200 hours of data, and this is good place to start with. This is all in English, I should say. This is a good place to start with. However, it's not really sufficient to train a production system on. To train a production system, you need probably on the order of 10,000 hours of data. That's over a year of continuous audio. It's a lot of data. Now, to bridge this gap between the data we have, this 3,200 hours of data, and the actual amount of data you need to train a production system, we actually introduced another project, which is called Common Voice. Common Voice is a website and an iOS app that's used to create open corpora, open speech data sets. Basically what we do is we present the user with a particular sentence, they read the sentence, and it's recorded. Then another user, in terms to validate this data set, another user is presented with the other user's sentence. They see the sentence there, and then they hear the recording, and then they can vote to say, yes, this person said the sentence correctly, or yes, they didn't say the sentence correctly. And once we created a big data set, we'll basically release the data set to the wild. Right now, we're started with English, but we're going to release in the next probably few days, I think, start collecting in German, French, and Welsh. And the site itself is actually localized right now to about 45 different languages. And we're going to start collecting these other languages too to actually help solve the problem of data scarcity for speech recognition. I guess now I'll talk a little bit about, say, future plans we have, and not in a huge amount of details, but to give you some flavor of what we're planning on doing or actually doing in the near future. I guess first, streaming. I mentioned earlier that the speech recognition engine uses a bidirectional recurrent neural network. This has unfortunate consequence of not allowing streaming, so one has to have the entire audio to actually get a transcript of. What we're doing now is we switch over. There's a PR really sitting in GitHub right now. There's a PR basically that switches from the bidirectional recurrent neural network to actually a unidirectional recurrent neural network, or just a normal recurrent neural network. And that's basically about to land really right now. And that should allow one to stream audio in and get transcript at the same time. And as mentioned earlier, in terms of privacy, to respect privacy and security, we're trying to actually get the speech recognition engine to work on small platform devices. So this requires us to do various different tricks. In particular, we're trying for Raspberry Pi as sort of our ultimate goal. It's hard to get on such a small device. But this requires us to sort of perform various different tricks with our speech recognition engine. One is change the architecture slightly to have a few fewer neurons. And other things we're doing is sort of rounding the weights of the neurons so we have fewer weights to actually deal with, and also doing quantization. So for example, instead of using 32-bit floats for the weight matrices, we can use 8-bit floats. Doing so, you don't really lose a whole bunch in terms of word error rate. However, the model gets smaller by a factor of 4. I guess that's really all I want to say now in terms of speech recognition engine. If you want to see the speech recognition engine, again, it's all open source. It's on GitHub. The code is there. There's the models there for English. And it's actually set up so you can actually train it sort of on your own. And also there's Node bindings to it, Python bindings, and C++ bindings, C++ bindings that are really right there. So you can download it and play with it on your own. And in terms of Common Voice, if you're interested in contributing or getting sort of the data sets that are there, that's under voice.mozilla.org. And if you want to contact me directly, I'm there also, kdavis@mozilla.com. So thank you. That's all I really want to say.